Hey everyone, welcome. Today, we're going to tackle a classic coding challenge. How do you generate every single possible arrangement of a set of items? We'll explore a really powerful algorithm that solves this problem with a surprisingly elegant and, more importantly, efficient strategy.
All right, before we really dive into the code, let's warm up with a quick question. If you've just got the numbers 1, 2, and 3, how many different ways can you line them up? Go ahead, take a second, because that is the exact problem we're about to solve systematically.
Okay, so here's the game plan for this explainer. First, we'll quickly define what a permutation actually is. Then, we'll get into the core of it, the swapping strategy. From there, we'll see how recursion makes it all work, decode the logic behind it, and finally, see why this whole approach is such a fantastic space-saving solution.
Okay, first things first, let's make sure we're all on the same page. What exactly do we mean when we say permutation?
It's actually pretty simple. A permutation is just a specific arrangement of a bunch of items. So, if you have the letters A, B, and C, well, ABC is one permutation. ACB is another. BAC is a third. It's all about the order.
And there you have it, the answer to our little warm-up question. For the numbers 1, 2, and 3, there are exactly 6 unique ways to arrange them. Each one of these is a distinct permutation. Our mission, should we choose to accept it, is to write an algorithm that can find all 6 of these automatically.
All right, let's get into the really clever part of this approach. See, a lot of solutions out there will have you creating new lists or using extra memory to keep track of what you've used. We're going to do something way more efficient.
So this is the whole magic trick, right here. We're going to generate every single permutation just by swapping elements around inside the original array. That means no extra hash maps, no helper arrays, which, believe me, saves a ton of memory.
So let's start with our good old 1, 2, 3. The strategy is to work from left to right, one position at a time. So, first up, we need to decide which number gets to be in that very first spot.
So, what if we want to give the number 2 a shot at being in that first position? Well, it's super simple. We just swap the element at the first position, index 0, with the element 2, which is currently at index 1.
And just like that, our array is now 2, 1, 3. The number 2 is now fixed, or locked in at the start. Now our problem is smaller. We only have to worry about arranging the rest of the numbers, 1, 3. And this one simple move, this swap, that's the engine that drives this entire algorithm.
Now, this is where it gets really cool. We're going to take this simple swapping idea and plug it into a recursive structure to explore every single possibility without ever missing one.
The intuition behind this is actually really straightforward. For each position in the array, we just want to give every single number a chance to be in that spot. And swapping is how we let them take turns.
And this whole thing follows a classic pattern you see a lot in recursion. It's called choose, explore, unchoose. First, we choose a number for the current spot by swapping it in. Then, we explore all the possibilities that come from that choice by calling our function again for the next position. And finally, and this part is absolutely crucial, we unchoose by swapping it back. We undo our change. That lets us explore other choices for the current spot. That unchoose step is what we call backtracking. Okay, let's walk through this. We start with 1, 2, 3. First, we choose to leave 1 right where it is at index 0. Then, we tell the algorithm to go solve the smaller problem for the rest of the array, which is 2, 3. And that little subproblem gives us 2, 3 and 3, 2, which leads to our first 2 final answers, 1, 2, 3 and 1, 3, 2. All right, once we've explored everything starting with 1, we hit rewind, we backtrack. Now it's time for a new choice at that first position. We swap 2 into the first spot. The array becomes 2, 1, 3. And now we do it all over again. We recursively solve for the rest of the array, 1, 3, and that's going to generate all the permutations that start with 2.
Okay, so now that we've got the feel for how this choose, explore, and unchoose journey works, let's nail down the actual blueprint of the algorithm.
This whole complex signing process really just boils down to a simple 4-step recipe. Step 1 is the base case. If our index has reached the end of the array, congrats, we've found a permutation, so we save it. If not, we go to step 2. We loop from our current spot to the end. In that loop, for each element, we swap it into place. Step 3, we make that recursive call to explore what happens next. And then, step 4, the most important one, we backtrack by swapping everything back to how it was. That's it. That's the whole engine.
So, you might be thinking, okay, this is cool, but why go through all this trouble with swapping and backtracking? What's the real payoff here? Well, let's talk efficiency.
Let's put it head to head.
Now, time-wise, it's going to be about the same as other methods. Generating n factorial permutations, well, it's just going to take a while. But look at the space complexity. That's where we get the big win. Other approaches often need an extra map or array to keep track of used elements. That costs O of n space. And then you have the recursion itself, which also takes O of n space. With our swapping method, we completely eliminate that extra data structure. We chop that extra space requirement right out. That's a huge win.
And that, right there, is the key takeaway. The real beauty of this algorithm is how lean it is on memory. By working in place, just messing with the original array, we have a solution that is incredibly space efficient. And when you're dealing with really big sets of data, that's an absolute game changer.
So let's leave you with this question, because this isn't just some abstract little coding puzzle, right? This technique for generating every possibility is a fundamental tool. It's used to solve huge, complex problems. Everything from finding the best route for a delivery truck to cracking codes in cryptography. The possibilities are, quite literally, ready to be permuted.